Good morning. Brian Tolino here, live from the APEX show floor. With me this morning, I have three distinguished panelists here to talk a little bit about miniaturization and advanced packaging. So firstly, to my left here, I have Rafael Padilla, who's the VP of OEM Marketing for Xingyi Technologies. To his left is Brian Schmaltz, who is the COO of Namix Technologies. And finally there on the end, we have Ram Chakor, who is the global head, market segment head for semiconductor packaging at Henkel Electronics. Thank you for being here. So glad to be able to discuss this morning. So let's start. Let's jump right into the questions. So I think a lot over the past few years, we've seen a lot of like mobile electronics, and now we see a shift towards more like AI or infrastructure, server type applications. How has that changed what you are doing at your companies with respect to material technologies, whether it be thermal or underfills or substrates? How's that change in the market affecting how you develop new materials?
Starting with me?
Sure.
Well, as you know, I'm with a laminate supplier to the PCB fabricators. So for us, what that means, especially what's going on with a lot of the shortages, specifically with ABF, due to NVIDIA buying up the majority of that for their packages, it's actually changing how they're designing their packages. They're going to like a co-op solution, so chip on wafer on PCB. So it's actually pushing the substrate spacing and technologies to the PCB itself. So for us, we basically have to come up with material solutions that can do what the substrates were doing with regards to spacing, with regards to those vias, but on the PCB itself. So for us, we've been, providing bonding films that can kind of do the same thing as what an ABF was doing, but in the PCB fabrication industry, right, to help enableize those solutions.
Ram or Brian?
Yep, so I've been with Namix for about 20 years now, and I can tell you that the packaging technology has shifted quite a bit. I've always been very accustomed to flip chip in general, but when I started it was 40 nanometer. So now we're talking, things dwindling in size significantly, talking about new packaging technologies from eutectic bumps down to lead-free bumps to copper pillar bumps to hybrid bonding. There's a whole bunch of different changes going on. I think when you're talking about heat dissipation, since that's what we're going to be kind of concentrating on with AI especially, that's a huge challenge. So trying to work towards how we're going to get heat dissipation out of basically a micro city that's embedded for device packaging, basically. I think something that we're constantly being pressed to do through smaller gaps, tighter tolerances, more heat dissipation, uniform heat dissipation, just to ensure that you get that good reliability and that good performance that the customers are striving for.
Yeah, so from a material supplier perspective, from Henkel's side, we see mobile and the AI data center applications bringing in two separate kind of pain points in terms of size and the value it creates for the end user. So in mobile side, it was always about miniaturization, cost optimization, throughput optimization. So there were a lot of challenges that we used to resolve for, let's say, wafer level packaging. Fan-out packaging, how to put things together in a small footprint, how to minimize Z-height reduction. But when you talk about AI and data center packages, now we're talking about very large body packages. Yield being one of the primary drivers, reliability being one of the primary drivers. The impact of materials failure on the value of the product is very high. So robust testing happens. Stickiness of a material is much higher in terms of once it's qualified, very hard to displace because they don't want to remove certain bond lines. So yeah, and like I said, I agree with the previous speakers. Thermal is a paramount challenge in AI and data center applications, where like the magnitude of thermal is probably 100x more in data processors when you compare it to a mobile processor. So yeah, those are the interesting perspectives that we get to resolve.
Yeah, I think on the thermal side, right, I think I've seen some numbers quoted like 1 to 2 kilowatts, right? So how does that change, I mean, obviously the tin materials have to change, but the whole cooling paradigm, like how is that changing with those types of numbers?
Yeah, maybe I can take this first. So right now we're at 1 kilowatt, moving into 2 kilowatt boundaries. So here the architecture is lidded or lidless architecture at the first level, moving into TIM 1.5 or TIM 2. Air-cooled works a lot in these things, but moving into like, hey, how can we extract into liquid? So it's still at a level, at a board level assembly, there is liquid coming in. But when we move into, let's say, about 2,000 watts, that's where we see architectures changing, where there is a liquid manifold directly in touch with the processor. There is architectures for damming certain liquids if it is directly coming into the SoCs. There's probably multiple choice of thermals, one choice for the memory and another architecture for inside the processor. We see complexities in lid manifolds, lid structures. As the package sizes go bigger and bigger, we see assembly challenges. Who does this assembly? Is it going to be at the OSAT? Is it going to be at the CMs? Who will pull in? Those are the challenges that we see in terms of thermal.
Oh, I mean, I agree with pretty much everything that was said there. I think, on a side note, for materials, when you're designing around materials, specifically with Henkel and Namix, we're kind of epoxy-based solutions, right? So, the one thing that's a challenge, of course, is epoxy isn't exactly a great thermal conductor. Mm-hmm. So, how do you optimize to ensure that you get a good epoxy with good thermal dissipation? And there's two different ways to think about that. You can do like a heavily loaded material, or you can even look at something like a metallic bond, right? Mm-hmm. A metallic bond, you're going to get a nice thermal dissipation path, and that's kind of what everybody's leaning towards in industry. And I highly recommend looking at those. But the challenges with that is die sizes and package sizes keep getting larger. So you keep getting larger, then you get more warpage during the thermal cycling. Mm-hmm. So then reliability becomes an issue. So it's a trade-off relationship either way you look at it. And like we were saying before, I think it is package dependent. It's design dependent, and there's a lot of different variables coming out. I'm hearing more about like you were talking about individual thermal coolers basically built on top of these structures, or hybrid bonded on top of them even, so you can help dissipate the heat. So I think there's a lot of challenges, and there's a lot of different options for solutions.
So related, I think on the substrate side, right, you're dealing with planarity, warpage, anything that you see in that space where that's changing your approach to the design or the material set that you're using?
Definitely. So because these packages are getting so large, there's multiple dies in the packages, you're dealing with a lot of warpage, right? So in order to counteract that, you need to find a way to reduce the CTE mismatch so that you can help with either the assembly or when these packages are trying to dissipate heat, so that you don't put as much stress on all the interconnects, the solder joints, things of that nature. So like I was saying earlier with the co-op solution, right, they're basically going to a glass interposer that will help match or get closer to matching the CTE of what you're seeing in the die, which will help reduce that warpage. Now, unfortunately, that kicks the can down the road to us in the PCB world, where we have to essentially attack that CTE mismatch. Luckily, because you're dealing with a PCB and not a substrate, you have a lot more layers to try to design a way to help match the CTE when those upper bonding layers, which are trying to do what the substrate did with such tight pitch, can try to help by maybe adding more glass to the bottom layers to help counteract that CTE mismatch. These are still questions that need to be answered, being that this is a very new way of looking at package design, but that's some of the things that are being reviewed and addressed to try to counteract those problems that trying to cool these packages are leading to, right? So.
Yeah, I mean, talking about the size, right? We talk about people going to like panel packaging or panel size, right? How is that affecting like the material offerings into that space? Like, you have to think differently when you're talking about materials that are going into a larger size panel versus, say, wafer sized or chiplet.
Yeah, I would say yes. From a supplier perspective, we need to think differently. First, we need to understand what is the panel used for. Is it used to make an interposer, or is it used to make the 2.5D assembly level at a panel? Both of these materials are going to be different. Or is the panel going to be more for smaller packages in mobile or other applications? All of these will require different materials. If you're making an interposer, then you need to dive down a little deeper. Hey, what is the process type? Is it a chip first type interposer or a chip last type interposer fabrication? Then you're dealing with situations like, oh, is it going to need an underfill component, or is it going to be just an encapsulation component? And if they're making just 2.5D assembly without RDLs, do they really need a liquid material, or is a sheet material better, or is a granular material better? So we think in multiple dimensions, but it first starts with, hey, what do you want to accomplish with it? What is the problem that you want to solve? And then we go into what is the right material of choice, properties, form factor, all that. Obviously, panel has a lot of advantages in terms of operational cost, in terms of scalability, yield, all that. So we create a lot of value, and materials truly make a difference in this. Yeah.
No, I mean, I don't have much to add on that. I was just going to say that, I don't think the design itself will change that much between panel and, wafer level or basically a panel or like a circular disc. So the one thing that you're going to get out of it, though, is, better yield. Because you're cutting up these interposers or these die, and they're all basically square. So you're going to have a lot more surface area, so you can actually manufacture them much more reliably, much more repeatably, hopefully. But that's something I just want to, I foresee that change happening. It has to happen to meet the demand that's in industry right now. So, to reach everybody, I think right now in this industry is, trying to max out their capacity as much as possible. There's such a demand from the major customers that we have to figure out a better way to manufacture, a more efficient way to manufacture. So I think panel is going that direction for sure.
So what are you as suppliers, like what are you doing to help those, the OSATs or maybe the further down the line? I mean, what are you doing to help increase that yield or help with the throughput? Like what are the levers that you have to help make that a better reality for the end customer? Yeah,
so I know that, most of us on this panel have pretty good experience across the board, not just materials. We look at ourselves as like a complete solution, right? So you want to be able to dispense to all the way to the end past reliability. And I think that's the key, is working with the customer and making sure that you can get from point A to point B as efficiently as possible based on the data that we have in industry. So, our experience kind of speaks for itself. We're able to, we're material solutions, we understand everything that is involved with optimizing the material, but it's also, like I said, the dispense. It's the curing, it's the things that occur downstream, right? So there's more warpage, of course, or less warpage with optimum designs of substrates. So things like that, and it's constantly fluxing and changing. So trying to think of a multivariable problem like this and solve it the best way possible is with everything coming together at the right time, I think is kind of tricky. But that's what we're working on.
Yeah, so from my side, maybe I can add a different perspective. So I totally agree with what Brian said. And another way to look at it is we see the process in which it's fabricated and the use. And if you see that, there are different ways in which yield loss occurs, in which failures occur. Like in a process side, let's say you're doing a panel molding or a wafer molding. If there is enough die shift happening through the process, hey, you're not going to yield as much. So how do we, as a material supplier, avoid die shift, provide a material that has stability for warpage, theta, XY control, and all that. And then if you look at field testing, there's yield loss or failures due to delamination issues, warpage, stress management. So fundamentally, how can we change material properties to improve adhesion to different interfaces? How can we offer stress management capability, warpage management? Again, thinking through the various materials in the interface, the various interactions, those are the fundamental studies that we do to create that value for our customers.
So many different options, right?
So many.
Well, I was going to say from my world being that we do produce IC substrate materials. For the most part, customers are trying to get tighter and tighter spacing, whether that be they're using a MSAP or a SAP process to try to achieve that. But right now in my world, it's a shortage issue in supply of materials. So they're trying to push those capabilities now to the PCB. And for us, that means we need materials with lower dielectric constants so that we can make them thinner. You can put more layers on the board so you can put more functionality and get more out of the package or more potential to improve the package itself. So, I mean, we're all material guys, right? So most of the time we're focused on how we can improve our materials to open up either your capabilities from a design standpoint or from optimizing it from an assembly standpoint or from a reliability perspective, right?
Yeah, so we've talked a little bit about like different package sizes and things like that. One of the things I'm seeing is a lot more of the optical components now moving from the edge of a rack, co-package optics or onboard, and spending a lot of time in optical spaces. That adds another set. We talk about CTE mismatch usually on terms of reliability, mostly in terms of solder joint cracking or something like that. But now you've got to worry about alignment. You've got to worry about the optical sort of components, and the temperature can also change. So how are you changing your approaches with respect to having a laser on board, having an optical coupler, dealing with waveguides? You know, how is that changing your approach in your space?
Well, yeah, that's actually a really good point. I've watched a couple of the NVIDIA presentations recently, and it's really mind-blowing when you start hearing about what's going on with NVIDIA and their communications, and then how they have to manually connect this giant fiber optic cable with multiple fiber optics on the back, and they have to be careful not to crush the components or crush the server rack. Yeah. So they're talking about more on board, and silicon photonics is going to be taking off for sure. But silicon photonics offers its own challenges. What kind of refractive index materials are you looking for? What kind of cure? What kind of reliability? Very different, but very, very necessary in the future. I think all that is expected to change very quickly, and the demand is there. I'm not sure if industry even knows what they want yet. So okay. This is kind of the chicken and the egg situation, where we can come up with solutions. We have ideas, and we test them out, but it's so novel that they're still trying to figure out a complete solution for it.
Yeah, so for co-packaged optics, from a semiconductor perspective, we see applications both in scale up and scale out areas. In the more near term, we see the optics coming onto the package, connecting the switch with the processor. So there, obviously, I don't see the lasers coming on board the package yet. It's still off package. So, but definitely alignment is a challenge. Having optical materials that are reflow compatible is a challenge. There's a lot of development happening. And then as we look 3 or 5 years out, now you're seeing disaggregated computing coming into play, where there's banks of memory, banks of processor, and now you need an optical interposer bed to connect the bank of memory and the processor. So that's where probably there's opportunities for new waveguide materials, new adhesives, optical underfills, because now you're removing the electrical layer completely and communicating with optics. So that's a new boundary that quite exciting. I hear there's a lot of inorganic materials in play, more in the waveguides than organics, but yet to see what the opportunities are and how we can shape it.
Yeah, it's actually, I was one of the questions I was pondering is, you know, there's a limit to organic materials. Right? We talked about thermal, like Brian, you mentioned earlier, like you've got to add filler to it. So where do you see a transition of maybe moving away from pure, and maybe this is a bit of a loaded question for companies that do a lot of polymeric materials, but, you know, I mean, there's a limit, right, to how you can do that. So do you change, are you looking at maybe not just epoxy-based systems, but other hybrids or other new filler technologies, or how you incorporate fillers? Like, what is happening on the research side that maybe will make, because we see this paradigm shift at the customer level, we'll call it, right? They're coming up with crazy ideas to try out. And so what are you doing on the material development side to really maybe have some sort of shift change? And maybe you can't discuss a lot, but I'd be interested in thoughts in general in that space.
Yeah, from a material supplier perspective, it's very important to look beyond what the current generation and the immediate next generation is, because if we look 10 years out, yeah, like you said, we may need a different class of materials, different class of fundamental raw materials. So what I can say is it's super important for material suppliers to work with our upstream vendors, with the other ecosystem players, really planning in what we need as toolboxes, capabilities to address these long-term pain points. It could be different fillers, it could be different resin systems, it could be a different way of even providing the product. So those are all the ways in which our formulation chemists and all that we work with, yeah.
So in my world, again, PCB, right? This discussion focuses more on backplane, midplane, or if you're going to get rid of that entirely to help the transceiver communicate faster with the GPU. And a lot of that focus right now is on whether or not we can get away with using like a PTFE type material build up with bonding films, like a hybrid stack up, large enough to be able to basically utilize and keep utilizing backplane or midplane technologies to help with the speeds that are required, right? And again, the question becomes, can those materials handle the type of reflow environments or the type of operating environments that you're going to see in this space in the next 3 to 5 years, where the speeds keep going up, the temperatures that you're seeing that need to be cooled down are more aggressive? Can these types of materials handle that? And what kind of fillers would you need? It's not like you would see with conductive, right? We're looking at hollow glass and things of that nature to try to, you know, load these materials to make them more stable and useful in this type of setting. But these questions are yet to be answered. I mean, this is the stuff that's going on today.
Just to add in on that, you know, it's not just technology also, but the other thing that always comes up is cost. I could take a, you know, an underfill material and load it with diamond, but nobody wants to pay that for diamond-filled underfill for nice thermal conductivity, right? And silver, you've seen the price of silver go through the roof recently. So I mean, all of these things kind of are trickle-down effect, and then we have to adjust according to the market as well. So it's a technology versus the price versus the market. It's a crossroads. That's just something I would like to highlight, especially. Because you know, we're starting to look at different fillers, different technologies, different solutions all the way through.
Yeah, and I think, like you were saying, Rafa, like you see stuff that was in the packaging world 5 or 6 years ago is now moving towards like board level, right? We see this, I don't know, kind of like pass-through technology or being pushed down. And usually those markets have different cost targets and different cost tolerance, right?
Correct.
So how's that affect? Like that also has to change. I think you kind of alluded to that a little bit, right? Like, how's that affect the approach? If there's larger volume, can that change that? Or do you need to come up with a different set of materials that maybe worked before, but now you've got to, because of cost pressures, now you're like, well, I can give you a solution, may not be the one you had before.
Exactly. No, go ahead. Yeah, no, I was going to say exactly. I think that's the kind of the key is it's based on the need and the demand. I obviously you want to tailor it to whatever the customer requires. So making sure that you can, if it's like a mobile device and there's a lot of mobile out there and it's very expensive to manufacture, very expensive raw materials, that's not going to be a very viable solution for people that have something for 2-3 years, that the shelf life of it. Yeah. But if you have like an AI system, I mean, that's completely different. There's a cost expectation, a reliability, and a performance expectation there that has to be met no matter what. So I think that's just...
Yeah, I definitely agree. If we're talking about a data center AI, 1, 2, 3% gain is a huge benefit when it comes to energy consumption, right? And these products are built to last for much longer than your cell phone. So the advantage that you gain from such a small percentage makes a difference regardless of the upfront initial cost that you're going to have to pay. So those customers are much more receptive to these types of changes versus someone that's building a cell phone or a consumer product. That's too impactful to them, right? The unfortunate truth is because the AI data center market is growing so quickly and the margins are so good for the suppliers that are making these materials on top of the benefits to the end customers, that it's completely changing the dynamic of our industry, where you're seeing shortages being put on those consumer manufacturers because the supply chain is becoming more focused on those types of products and those customers that are willing to spend that money because the advantages they gain far exceed the upfront costs, right? So it is forcing these consumer manufacturers to look at their designs and try to find a way to still get some of those advantages without having to spend the same cost, what makes it very tricky for folks like yourselves that have to try to play in both worlds and can't pick or choose some of these winners and losers. So definitely agree. It's quite a challenging problem today, but it's a great time to be in the industry, if you ask me.
All right, so let's do one final question here. The next 5 years, why don't you give me one thing that's super scary and one thing that's super exciting that you see on the horizon? And maybe they're the same thing.
It's the same answer. I'm going to say it's AI. I mean, it's amazing what it can do, but it's very scary as to what it can do. I mean, we've all seen the movie Terminator, right? I mean, that is obviously the scariest part of what you can get out of this. You can start seeing robots that can perform as well, if not better, than human beings. And that could be used in a very negative way or a very positive way, right? So it's kind of a double-edged sword. You have some really cool advancements that can come from that, but some very scary propositions that can also be utilized by, depending on the type of people you have in power or, I'm sure you can imagine. So I think it's the same answer to that question is it's AI.
Yeah, maybe I can take this. So the scary part is how the world is changing, in the next 5 years or 10 years, are we going to have 5 different ecosystems that we need to supply to as a global company? Do we need to set up operations in many axes? That's the scary part. Hope we don't get to that situation. But the exciting part is the amount of opportunity that is available for all of us just because of AI and all the new things that it's going to be possible.
Yeah, I answered that question as a personal perspective, not from a supply perspective. I agree with you from a supply perspective.
It's it's a good answer. But
sorry.
I think we hit the tip of the iceberg is what I'm trying to think. And the most interesting thing to me in the future is AI is ramping right now, right? And everybody's talking about server processing and everything like that. IoT is going to come back huge. So there's going to be an Internet of Things and devices that are going to change the world. That's going to be plugged into the ecosystem that's going to be created. And I think in the next 5-10 years, you're really going to see that. I mean, I would be shocked if 10 years from now, everybody is still staring at a phone.
Yeah.
I think phones are going to be obsolete in 10 years. But you're already seeing it with Meta glasses. There you go. So, it's just going to happen in the future. People are going to get tired of staring at phones and carrying phones. And that's just one item. So on top of that, you're going to see more wearables, watches, more things that are integrated with an ecosystem. So I think you're looking at a complete change in technology in the next 10 years again. It's going to be 5-10 years. It's going to be crazy.
But I think it's not. They're not going to go away.
No, they're not
change,
going to go
right?
away.
Because like
right.
No, they're gonna-
laptops
yeah.
don't go away.
Right,
Because
right.
we've got like it adds another layer, another thing that we're going to interface with
Exactly.
in a different way, and each of them will get their own kind of like use case. Right?
But I really like his comment about, from a supply perspective, we're going to have to make decisions on where we want to invest our money and looking at the risk of whether or not that's going to take off, right? And we're at a time where things are moving so quickly that it's a lot easier to make those decisions because you can see the advances that are happening. You know you're going to be needed. So I think it's a really cool time to be in this industry, where in the past there was so much more focus on risk mitigation, on spending any money on R&D. So this is what's actually moving the industry so much quicker than we've seen in the past because of what we can all see from what's happening. We know it's coming, right? We know our phone, it may not be obsolete, but it's definitely not going to be as important as it used to be with all these other advancements that are coming. We're going to have some other cool toys to play with. And, it's a great time.
Yeah. No, I think that's great. I really appreciate the discussion today, and I think it was really informative, and I hope folks out there watching and listening either today or in the future get a lot out of it. I'd like to thank our panelists here again today for a really engaging and interesting discussion, and appreciate the time.
Thank you for having us.
Thank you, Brian.